Hey, chemistry. Today we're going to go through a couple different ways to classify the periodic table. The periodic table is our power tool. It's a chemist's power tool. It's so packed with information and patterns. You just have to know how to use it, and it becomes this lifeline for all chemists. So we're going to get into a couple different ways to classify the periodic table, and we'll start to unpack all the information that's inside that is available for you guys to use. So we're going to start by going through just a couple really basic classifications. And the first is going to be representative transition and intertransition elements. So we make this distinction between representative elements, transition elements, and intertransition elements really based off the electron configuration. And so to talk about representative transition and intertransition elements, I'm going to box a couple things, and you may notice something suspicious about what I box. Okay, so these elements are the representative elements. So if I'm coloring some boxes for the representative elements, I'm going to box these things. Transition elements are going to be these right here. These would be transition elements. And then inner transition are going to be these, the lanthanide and actinide series down here. Okay, so after I have boxed representative transition and intertransition elements, you may notice something interesting. Anybody notice? The representative elements are the S and P boxes. The transition element lines up with the D box, and the intertransition lines up with the F. And this is exactly this explains exactly why they fall where they fall also. So we're going to start to use representative transition and intertransition elements as we start to talk about ions that form and also bonds that form. And what you'll start to see is the exchange or the interaction that happens between atoms happens within these boxes when representative elements react together or react to form ions, that the electron behavior that causes the bonding and the formation of ions, it all comes from the S and P orbitals. And the transitions, when they react, when they form ions, a lot of that activity happens within the D orbitals. And so we start to see that these labels are very linked to these boxes. So shade your periodic table. Make sure that you have this as a reference, because we're going to start using these terms, and sometimes you're going to want a quick reference to go back to figure out where the representative elements are, where the transition elements are, where the intertransition elements are. One other note, sometimes we call this box here in the middle, sometimes we call them transition elements, and sometimes we call them transition metals, because this whole box contains metals, as we're going to see on one of the next slides. Okay, let's keep going. Representative groups and families. So on this slide, we're just going to look at the representative groups. We're not looking at the transition elements. We're not looking at the intertransition elements. We're just looking at the representative groups. And so when we're talking about the periodic table, as we've talked before, rows on the periodic table are called periods. As we start to study why the periodic table was arranged the way it was by Mendeleev and the scientific community, and what kind of things repeat throughout the periodic table, you'll notice that those patterns repeat within a period. They are periodic, right? There are lots of things that are periodic in our lives. Time is periodic. The clock goes all the way around and then it starts again. Seasons are periodic, right? We go through spring, summer, fall, winter, and then it starts again. Spring, summer, fall, winter. Our classes are periodic. We go through second, fourth, sixth, eighth period, and then it starts again and goes through it again. Well, this happens on the periodic table also. You go all the way through a row, and then patterns start over. All the way through a row, patterns start over. So that's why rows on the periodic table are called periods. Columns on the periodic table are called families. And we start to see why they're called families when we look at the families themselves, some properties inside them, and then their electron configurations also. So let's start to look through these representative families and see why that's the case. So each of these families, each of these columns, if you study the electron configurations, they repeat in a pattern. So we drew a periodic table before that had all the electron configurations, the very last electron to go into that atom. We had that written out for at least the first 4 rows. Okay, and that periodic table looked something like this. Okay, so notice the person who made this periodic table took helium and moved it over. So this actually is helium. Okay, but notice on here that when we write out the periodic table and we replace the symbol with the very end of the electron configuration, we notice some big patterns that happen, right? This whole first family has the very same end of their electron configuration. This whole first family ends with an electron configuration that starts with some number. I'm going to put N instead of some number, and then an S, and then a 1. So that's how we can represent this family. We can represent it with kind of a code. Instead of putting the energy level 1, 2, 3, 4, 5, 6, 7, we can put an N, and that way that code represents the entire family. So this family is actually called the alkali metals. They have to do with bases or alkaline substances. They were originally recovered from ashes, and that's where the word alkali comes from. Alkali means ash. I think it's in Latin, something like that. And this whole table is called a family because their electron configuration is so similar. When reactions start to happen, reactions happen because of valence electrons. Valence electrons drive reactions to happen, and they determine how elements are going to react. And since this whole family has a very similar electron configuration, they're all going to react very similarly to one another. They're all extremely reactive. The alkali metals are all extremely reactive. And in fact, when you find them in nature, you almost always find them in compounds, not elements, because they're so reactive. Okay, let's take a minute then and try to write the code for the second family. This second family right here. Pause the video here, see if you can write the code for this second family. Okay, this second family, they are the alkaline metals. And their family code would be N instead of the energy level, and then S2. And again, They are going to react all very similarly to one another. They're also fairly reactive, not quite as reactive as the alkali metals, but fairly reactive. And they all form similar compounds to each other because they have the end of their electron configuration the same. Okay, before we move on further, I want to point out one more thing to you. On the top of the periodic table, you're going to see the columns usually numbered in a certain way. So this periodic table has the columns numbered 1A, 2A. Notice all the transitions are B's, and then you have these as well. This should be an 8A. This family should be 8A. Okay, and so notice at this point in time when we look at the code and we look at the number, that label on top of the column, we can see something. What do you suppose the label on top of the column is indicating? One what? And hopefully what you'll see is that it lines up with the code for the family. So it's a NS1, 1A, NS2, 2A, right? So we're going to skip the transitions. Remember, we're just dealing with representative families, right? We're going to skip the transitions for now and go to this family right here. And that family right there is also going to have a code. Now, this code is a little bit harder because the entire code is not written out in this square. So the code has to incorporate all of the valence electrons. And valence electrons are going to be all the electrons in that energy level, in the outermost energy level. So remember, S and P are not energy levels. Energy levels are 1, 2, 3, and 4. So the code for this family is going to be is going to contain all the electrons in one energy level. So in order to write the electrons for that energy level, you have to include S and P. So the code for this family, let me kind of delete some of what we have here, make it a little bit nicer. I'll write the code down here. So this is NS1, this is NS2. The code for this family, the 3A family, has to include the S's and the P's. So it's going to be NS2 because all of these have their S's filled, and then NP1. And again, that can represent any of these. If we're representing this element right here, which is boron, we would write 2s2, 2p1, right? If we're going to represent this element right here, which is aluminum, its valence shell would be 3s2, 3p1. So because the energy level changes for every element within the family, instead of writing the energy level out, 2s2, 2p1, 3s2, 3p1, we're going to write an N in the place of that, and that is the family's code. Now, this family doesn't have a special name like alkali metals or alkaline earth metals. At least it doesn't have a very common special name. And so for anything that doesn't have a super common special name, we just call it the family of the first element that's in it. So the first element in this family is boron. So we would call this the boron family. Okay, so now pause the video here, see if you can write the code for the 4A family. Okay, the code for the 4A family would be NS2, NP2. And notice again, 2 plus 2 equals 4. So that's where that code comes from. That's why it's the 4A family, because it has 4 electrons in its valence shell. Now again, this family doesn't have a special name, and so we would go to the first element in that family, which is carbon. So this would be the carbon family. Again, I'm going to delete this and make it a little bit more readable, and I'll write the codes at the bottom for you. So while I go and do that, why don't you guys try to write the codes for the 5A, 6A, 7A, and 8A families? Okay, 5A is going to be NS2NP3. 6A is going to be NS2NP4. 7A is going to be NS2NP5. And then the 8A family is going to be NS2NP6. So notice, for this family over here, which does include helium, NS2NP6 shows you that the S shell is holding as many electrons as it possibly can. The P shell is holding as many electrons as it possibly can. Both of these shells are filled, and so this family is going to be super, super unreactive. It doesn't need to gain or lose electrons in order to be full, so it's not going to be reactive at all. And this family, the 8A family, is called the noble gases. There's actually two other family that have special names. You only have to know one of them. The 7A family, they are known as the halogens. They are also very close to being filled. Notice NS2NP5 is only missing one electron to be filled, and so they're going to be super reactive also. And then the 6A family kind of goes with two different names. So sometimes they're called the oxygen family because oxygen is the first one. That's probably their most common name, the oxygen family. Sometimes you'll hear them called the chalcogens. So that they do technically have a special name, but hardly anyone uses it. And then the 5A family is just called the nitrogen family. So there's really only 4 families you have to know that have special names: alkali family, alkali metals, alkaline earth metals, halogens, noble gases. And then all the other ones you can just call by the first element in the family: the boron family, carbon family, nitrogen family, oxygen family. Okay, so those are all the representative families. Now let's go on and look at one other way of classifying the periodic table. All right, and that is with metals, nonmetals, and metalloids. So this classification you might be the most familiar with of all of them. Hopefully you have looked this up if you're not familiar with them. So there's this little stair step here in the middle. And this stair step tells you the metalloids. So these are metalloids. And then everything on this side, including these down here, all of these, and including the lanthanide and actinide series, all of these, they're all metals. And then the nonmetals are on this side. So the vast majority of the periodic table is what? The vast majority of the periodic table are metals. Almost all of the elements on the periodic tables are metals. There's a few metalloids, very few, and then there's a significant handful of nonmetals, but the rest of them are all metals. Now, what is the difference between metals, nonmetals, and metalloids? So I'm sure you've talked about this before. I want to take a minute and recap what you know. So tell me, Now would be a good time to pause the video, try to fill out this chart. What do you already know about metals, nonmetals, and metalloids as far as their conductivity? So conductivity means their ability to transmit heat and electricity. So energy. How good are they at passing on energy? Luster is another difference between all of these. Luster is a scientific way of saying shiny, their shininess. Phase at STP, phase is going to be either a solid, liquid, or a gas, and STP just means standard temperature and pressure. So you can imagine like room temperature. The room that you're sitting in, most metals are going to be what? Most nonmetals are going to be what? Most metalloids are going to be what? Ductile and malleable are these funny terms that we always go to when we're classifying the properties of these three things. So ductile means its ability to be pulled into wires. Malleable means its ability to be hammered into a sheet. So basically, if you hit it with a hammer, what's going to happen to it? What's going to happen to a metal, a nonmetal, a metalloid? And then relative amount. So this is talking about on the periodic table. Relatively on the periodic table, are there a lot of them? Are there a few? Are there a handful? What do we have? Okay, so pause the video here, fill this out, see what you can do. I like to start with the metal family because metals, yes, they are conductive. Metals conduct heat really well. Metals conduct electricity very well. Usually, if you're looking for a conductor, you are looking for a metal. Metals, the vast majority of them are shiny. Not all of them. If you ever see calcium metal, if we ever get back to into class, I can show you calcium metal. Calcium metal is not shiny, but most of the other ones are shiny, or at least they can be shined. A lot of metals form a very protective coat over them very quickly, like your tinfoil in your kitchen. When you pick up tinfoil, it's actually aluminum foil. You're not picking up solid aluminum. You're picking up solid aluminum that has been coated with this very thin coat of aluminum oxide. And as soon as you rip it, that new aluminum that's exposed coats itself right away with aluminum oxide. And so aluminum would be shiny if you could get it to stop reacting with oxygen, but it's really hard to do. You would have to fill your atmosphere with argon, completely evacuate all of the oxygen, and then rip it apart, and then you would be able to see how shiny it was. So some of them don't look shiny, especially because they form this protective coat of oxides, which it actually isn't shiny, but most metals are shiny. Okay, most metals at STP are going to be solids. There's only one metal that's not a solid at STP, mercury. I'm sure you could have guessed that. Malleable and ductile. If you hit metals with a hammer, it bends. So yes, metals are ductile. They are able to be pulled into wires. Yes, metals are malleable. If you hit them with a hammer, you can pound them into a sheet. They don't shatter. And then, like we just said, most elements on the periodic table are metals. Okay, let's go to nonmetals next. Nonmetals, I like to call the not group. Nonmetals are not conductive. In fact, nonmetals make really good insulators because they don't conduct heat and they don't conduct electricity very well. Metals are not shiny. In fact, metals tend to be the opposite of shiny. Some nonmetals can be cut to reflect light, and so they can be cut like diamonds or quartz to be sparkly, but they don't naturally most nonmetals don't naturally reflect the light in the way that metals do. Okay, at STP, nonmetals are actually very confused. Lots of nonmetals are gases like oxygen, nitrogen, most of the halogens at STP, most of these are gases. Some of them are liquids, like bromine is a liquid. Elemental bromine is a liquid at STP. And some of them are solids, like lots of forms of carbon are solid at STP, phosphorus, sulfur in their elemental forms, even iodine in its elemental form is going to be a solid. And so we see a much bigger variety of nonmetals. And this comes down to boiling point. At what point do these things boil or turn from a liquid to a gas? At what temperature do these things melt? Do they turn from a solid to a liquid? And metals are much more consistently high. Metals have extremely high melting and boiling points. Nonmetals are variable. They can take on a lot of different structure in their solid forms, and so therefore they have a much more variable melting and boiling points or temperatures at which they undergo these phase changes. Metals are not ductile and malleable. If you hit a nonmetal with a hammer, the chances are it will shatter. And there is a relative few amount of nonmetals. You saw it was kind of that like corner on the periodic table. Those are all the nonmetals that exist. Okay, and metalloids are a really interesting category too. So metalloids tend to be kind of like the black sheep of the periodic table. Anything that doesn't clearly fit within the metal and the non-metal category kind of gets fit into this metalloid. So there are the least amount of metalloids, and then they have a mix of properties. And actually, that mix of properties is not very consistent at all. So some metalloids are shiny, some are not. Some metalloids are conductive, some are not. And it's not consistent through them. One metalloid might be shiny and conductive, but not malleable. Another metalloid might be malleable and shiny, but not conductive. So all the metalloids kind of take on their own personality, and they don't really fit super well into one category. And this can be a big strength of metalloids too. Some metalloids like silicon is like the backbone of technology because it has such unique characteristics that metals don't have, and neither do nonmetals. It's this like beautiful mix of properties that can support a lot of different like electronic engineering. And so the metalloids don't fit very well into either category, but really that's their strength. Okay, so we've covered a lot of information. Hopefully you have some periodic tables colored that you can refer back to. You know a little bit more about all the groups. We'll continue to unpack this periodic table. Like I said, it's this amazing tool, and the more you learn about it, the more amazing it gets. So bring your questions to class. Let me know what you wonder about, what you're confused about. Let me know what your questions are, and I will see you in class.